Hello everyone. Today I'd like to give an introduction to OpenMP parallel programming. So my name is Jamie Hu. I'm a SHARCNet HPC consultant based at the University of Waterloo. So I will start with a simple review of parallel programming concepts, and then we'll introduce the OpenMP concept. So the core part of OpenMP is the OpenMP compiler directives. So today I will only be able to cover the basic parallel region and the work sharing constructs. And I will briefly mention the others, and most of them were important thing is I will give reference and for you to find more information and how to do real OpenMP codings if it's really needed for your research. And finally, I will show. I want to give you an idea the SHARCNet systems and the compilers and how to run OpenMP code on specific SHARCNet systems. Okay. First of all, when you're running your parallel code, you would like to know the basic hardware memory architectures. So here, I showed the simplest one. It's a shared memory solution. So shared memory machines vary from one to the other. There's many different hardware shared memory systems. So it doesn't matter how they are built, they are all in common. They have the ability for all processors to access your data in one memory block. It's normally called a global memory space. Some systems, they may have more CPUs, so modern hardwares, they use developer, the so-called fat load. The load will have many CPUs, and the memory code will have a big chunk. It varies from small size to a big size. So in this type of hardware, the multiprocessors can each operate independently. They can do their own computations. However, because they mostly they share the same memory resources, so they work on one data set, one copy of your data. So in the case, the changes in memory location affected by one processor will affect the data in the memory location and is visible to other processors. So this type of machines is quite common nowadays, and even your laptop is a shared systems. You may have 4, you may have 8 CPU cores on your laptop, and workshops is a typical shared memory systems. And the other one is actually for big systems like clusters at SHARCNet or big systems in any HPC institutions. So it's so-called the hybrid distributed shared memory architectures. The cluster could be big. It could have hundreds or thousands of nodes, and each node is a shared memory, small shared memory systems. And we call it is a shared memory load. And again, and it varies from system to system. At SHARCNet, we have the old systems only have 2 CPUs per node, and now we have systems with 32 CPUs per node, and it's a block of shared systems. So you will know, and many of you are using running parallel code at SHARCNet or in a lot of HPC institution. So it's basically for cluster where each node are connected via the internal network. And it's basically is a distributed solutions. And when you do the communications for data on different memory location, well, you need to do the communications between the cores at your software at your programming side. And here we only talk about, well, give you an idea is say, well, we're talking about shared memory solutions. So what your code can run is only or limited to run on one specific load. Okay? So parallel computing, what is it? Well, you want to do parallel computing, or it's basically, and there's many reasons, and simply speaking, you can put in these two ways. So you either want to decrease the runtime for solution to a problem. Say your code may have to run for weeks, and on one CPU, the traditional one. And say you want to, if you use 100 CPUs to run your code, you hope it can be finished in hours or in days. And the other approach is say, well, you want to increase the size, the data size of your problem, and it normally cannot be done with one CPU, the traditional one, and then you want to have more power to make use of multi-CPUs. So in general, simply it gives you more performance to throw at your problems. However, while parallel computing doesn't come simply and cannot fully supported by the hardware, so basically you need to do the programming on your side. And the program sometimes is easy. It depends on what type of problems, what type of research are you doing. So basically, well, you need to know which part you need to parallelize it. Well, for some is a full parallel solution, some are partial parallel solution. So you need to specify the parallel executions in your code. And then the other one is because you want multiple CPUs or multiple threads to work on your problems, and you need to figure out the communications between multiple processor and threads. And finally, you want to do a good synchronization because each CPU or each thread, they work their own, work on partial of your data. And finally, you want to synchronize it and to do it right, and the final results will be right. And many issues maybe you need to be considered, and you need to consider it. And some of them is easy, some of them are not that easy. So we're talking about sometimes is data parallelization or task parallelization, and then we talk about do you want to do coarse grain or fine grain parallelization? Well, it all depends on what type of problems do you have and what type of goals you want to achieve. And the most common concept is the distributed parallel solution or the shared memory parallel solution. The distributed parallel memory solution is popular now, and the approach is basically the MPI, the message passing interface. It's a library-based interface, so some of you, I think you're good at MPI, you understand the full concept of it. And it potentially can make use of many CPUs to do your work. And it's basically the code from start to the end is a full parallel approach. And the other way is shared memory systems. And what we're talking about today is the OpenMP, is compiler directives. And the other way still quite popular is called the P-thread. So it's the same idea and basically the same program model and different, little bit different programming syntax. Okay. So now we introduce the OpenMP concepts. And what is it? Well, it's simple. Put one sentence is an application program interface, and that may be used to explicitly direct multi-threaded shared memory parallelism. It uses compiler directives, library routines, and invariable variables to automatically generate threaded code that can run in a concurrent or parallel environment. And then it's portable, and then the API is specified for C, C++, and Fortran. So this is the difference from the P-thread. P-thread is basically only for C, C++. So OpenMP extend P-thread concept and make it easier and make it more useful for other software like Fortran, because C, C++ and Fortran are still the two major languages used in science and engineering computings. So it's actually multiple platform has been implemented, including most Unix, Linux platforms. And originally, it actually tried to work on Windows NT as well. And it's a standard approach. And the people from the major computer hardware and the software windows come together. They agree to define the same set of interface and encourage all the companies to come together to work together and make sure it can be portable to all type of hardwares. And the compiler company are supposed to come together to support it. However, still different compiler, they may have a different approach, but basically they support all the functionalities. So I will encourage you, if you are more interested about OpenMP, and there is a website, it's called openmp.org. So the OpenMP, the first stands for Open Specification for Multiple Processing. So here is a basic OpenMP solution stack. So it says, well, the hardware itself is a shared memory hardware, and it doesn't matter how many CPUs or how many cores the hardware have, they should have the ability to share a memory. And then on the systems level, the operating systems and should support for shared memory and the threading. And then it supports for OpenMP runtime library. So this is basically the part supported by the compilers. So the compiler should have the ability to support for the OpenMP the interface. And then on the program side, and well, it's basically three parts. Either is the directive or the compiler library. So this part you need to be done on the software side, and is supported by the compiler. And then you have your own applications and then for you, you just need to understand the problem, understand your problem, which part need to do parallel, and then use the right directives or the right OpenMP functionalities, and hopefully it will do a good job for you. So why do you need to use OpenMP? And well, certainly, well, if it benefits for you, you will use it. Otherwise, you will not use it. So that's the basic thing for you to go further step to use to parallel your code. So the benefit of the first one is standardized, and because well, you have the code pretty much will work on all kinds of shared memory hardwares, as long as the hardware has the right components to work on it. And then the most important thing is, well, he says near and mean. It's simple. Well, in normal case, you may only need to use a few OpenMP directives and to work on your sequential code, and or basically let your sequential code to run in parallel, use multiple thread. Or either it runs good or not is not an issue, and this is the most simplest way to transfer a sequential code to a parallel code. And then, well, it's portable because it's supported for basically all Fortran code, and it's supported for C and C++ code as well. And then you can easily find support and find the different specifications from the public forum for OpenMP. And the OpenMP web page listed all the specifications. Well, it's a big documentation. It's up to 400 pages. And for simple use, maybe you don't worry about that too much. But if you want to use it extensively and you want to use it smartly, you may like to take a look at the API defined by an OpenMP group. Okay. So here is the simple OpenMP Hello World code. I bring up this is want to show you the basic things you need to use, and for the very simplest code. So when you have a C code, where you always you need to include the header files, and then you have a main code, and then you have some definitions, and then you have printing whatever operations. If we transfer that to OpenMP code, and here is basically several parts you need to include it in. The first one, well, is OMP.h is a header file for OpenMP. And the most important part is this is OpenMP parallel. So this is in C syntax. So in C, you always start with this program OMP, and tell the compiler this part of the code I want to run in multiple threads. And the parallel is the parallel region constructor, and to start a team of threads for the code. And then it comes with library routines, like each thread need to know the ID itself. So in OpenMP is or OpenMP get thread number, and then do whatever and by each thread. And here is a synchronization constructor and the barrier. So all thread will stop here. And here, well, because each thread has a different ID, and you can say one of the thread to do something, and the other thread basically they don't need to do anything. So here, say if the thread ID is 0, we sometimes call it the master thread, and then say this will be get number threads. We'll know and how many threads I'm using to run this part in parallel, and then you can print out this simple one. So this is the simplest code, and basically giving you an idea what's actually needed for a simple OpenMP. And you basically add some OpenMP parts on top of your sequential code, right? So if we put it in a general way, the syntax for OpenMP code, it always looks something like this. So you have a sequential code, and the sequential code, you build it up, use OpenMP. So you need to include an OpenMP header file. And then at part of your code, you want to run in parallel. It's at that point, and you start with the OpenMP. And there's some other is the data structure or something like that. And then this part, or if it's it will run by multiple threads. And at the end, all threads should join the master threads and do the synchronization. And then after that, or your code come back to sequential code. So it's always like a partial or parallel solutions. So the syntax will start always in C, starts with this, pragma OMP, and then this is a parallel is a directive name, and then you have different data controls of your variables or data structure. So in Fortran, it's the same structure, but where it's slightly different in terms of the syntax. So in Fortran, it always starts with the singular is this type of OMP, and then it still is a parallel and blah, blah, blah. Okay? So we can put it in a short review. So OpenMP and basically is a fork join parallel solutions. So your code is always started with a sequential code. It's run by one CPU, and in terms of OpenMP, you can say it's run by one thread. And at some part of your code, you want it to run in parallel, so you call OpenMP parallel to create a team of threads to work on that part of your code. And then at some point, you say, well, maybe your code cannot run in parallel, and then you come back to sequential code, and then the other part you may want it to run in parallel as well. So it's this is serial parallel, that type of model. Okay. So the components we mentioned earlier is basically 3 of them, and the big part is the container directives. That's the core part, and then is a few library routines, or you can set that library routines as environmental variables, such as you can set up the number of threads to use, and you can set up the way it does, such as the regular one, or you want to do it in dynamic threading, or you want to do listed parallelization, those kind of things. And in terms of directives, and I will cover it, I will start next slide. So it's basically, there are 5 different categories. The first one is always start with the parallel regions. And then the basic one is work sharing constructors. And then there are some others is more detailed to actually let you do your work right. And it's a shared memory model, and normally we talk about where your main data is basically one copy. and all threads will work on that one copy. And it's shared for sure. In the meantime, each thread sometimes needs some certain control, and they cannot be shared. So each thread can have a small stack memory, and it's called private, such that the ID is not shared. Each will have its own ID, so ID is always private. And some other data, maybe you want to keep it a copy for each thread to work on it, and because the big issue will be the data chase problems for when you work on shared one copy of your data. So it's shared memory. So in terms of the data definitions, well, you can have some private variables, private data as well. It depends. Okay. So now we can move on and to talk about the directives. So we said, well, we can roughly classify data constructors and into 5 categories. So the parallel region, work sharing, and data environment, synchronization, and then finally is the runtime function and variables. And all those can be used in Fortran or in C++, and slightly different syntax, and different language may have different syntax. Okay. So if we come back with this simple example, what it usually actually uses the parallel region constructors we call the parallel. So the main purpose and for it is actually to start a team of threads for the code, right? For the code to run in parallel. So this is always needed in OpenMP. So it's the basic one, and but it's sometimes where it's too simple, where maybe you cannot only limit it to use it. So it's basically the function for it is create a team of threads and to run the code whatever in this block. Okay. And the more important one is for the work sharing constructor. And the work sharing constructor is actually, well, you want your work to be shared by a team of threads. So the parallel region already give you a team of threads, and then it's up to you to how to divide the workload to each thread. So this is the work sharing constructor will do for you. So the motivation is something like this. For example, you have a sequential code, and then you have a loop to run some tasks, right? And in work sharing constructor, you want to build your code as simple as possible. With the parallel region, where you have a parallel region, create a team of threads, you can actually manually force which threads to do what. For example, simply for the loop, you can actually control the loop index and to force each thread to do a part of your computations. Yeah, that's possible. Use work sharing constructor will simplify that process. Where, for example, here is basically for the loop parallel 4 is where basically the compiler will do the work for you, and hopefully it will do good work. Okay. So when we talk about work sharing, normally we talk about the parallel loop, and that certainly is the big part. It actually has some other things, and in terms of definition, the other one is called sections. So sections will break works into separate sections, and each section can be executed by one thread. So this is a sort of called functional parallelism, or sometimes you can say it's a task parallelism. And the loop is more likely as a data parallelism, something like that. And certainly it's not exactly right by definition. And the single is something, sometimes it works likely the master thread is actually put it to be work sharing constructors. So work sharing constructors, one, as I said, is for a loop constructor. And its syntax is easy. You have your original loop. And then in terms of C, well, here is basically parallel is open a team of thread for your code to run. And then you use program OpenMP is for the compiler to tell the systems to run your loop automatically by multiple threads. In Fortran's case, well, it's dual loop. This loop is where you have a parallel do, and this is will do the same thing. And then the other one is the section directives. And section directives, as I said, well, it's a long iterative work sharing constructor. So it specifies which part the code need to be done by one thread. And each individual section directive is nested with sections directive, and each section is executed once by thread in a team. So we'll put if we have a simple example here, you will understand it better. For example, if you have a code and you have several dual loop to run, and you can certainly use the loop parallelism to parallelize each loop separately. That normally is the case, and pretty much that's the approach you want to go. However, if say your loop, each loop, the workload is not so different. Say if they have similar workload, you can actually let one loop be done by one thread, the other loop be done by another thread. So that's the other way you basically parallelize your code. So in this case, as you know, we have three dual loop, and each of them have similar workload, and then we can use OpenMP to parallelize use the sections. So in the sections, you need to do is you to add sections, tell the compiler I have several sections to come. And the compiler will say this, or this is section one, or one thread will do this part. The other thread will jump and will pick up this part, and the other thread will pick up this part. If you have more sections to here, and you have few threads, where the threads will finish the one, will pick up the next one. If you have more threads and only have 3 sessions, well, the other threads basically idle there don't need to do anything. So this is just another way to parallelize a code. It's another approach. Or either it's practical in your case or not, it's the other thing. Okay? And then the big part in OpenMP is the data scope clauses. So this sometimes is the difficult part, because the big problem is OpenMP is the data race. You have one copy of your data, and you want to do it right. You don't want each overwrite it and chase each other. So you need to nicely to specify which part is shared and which part has to keep it private. And then on the thread side, you want to, well, maybe you want to use thread private or whatever. So this part is something you need to study more and to try to to fix problems if your set of final results is not right. Start from simple things and work along. And it has some nice sense for simple operations, such as they have copying and they have reduction operators in OpenMP. That will do a good job for reductions. Okay. And then in terms of synchronization, they have several ways to do it. And sometimes if you work on specific data arrays or something, or you can do atomic. It basically let one thread do it, and the other threads basically wait to do other things. Or the critical sections. And the barrier is the most expensive synchronizations. Sometimes you have no way to deal with it. Maybe you have to use a barrier to let all threads to wait at a certain point. And there's some other things as well. And order rate is basically you force all threads to wait and let it works in a sequential way. So there are some ways to control it, and some good part and some bad part. Synchronization is always expensive, and slow down the whole process, slow down your computations. So you will like to use it nicely. Well, again, it depends on what type of code do you have, what type of operations do you use. Okay, and then we can use this example to show you and transfer a sequential code to OpenMP and a parallel code. So the sequential code in this case is basically is the simplest one. Say we take this approach and the numerical integration of the pi. So in this case, where you can always different ways to approach it, and the simplest way is the discretization. So it's basically you transfer it to be a sum of the areas. And in this case, where if you cut it to different part, and assuming each thread work on one part, and if you cut it to very fine grid, and the results could be good, right? Sequential code is simple. You basically have one loop. You start from 0 all the way, and you finally you add them together. That's it. And OpenMP is not difficult as well. So it's basically you have exactly the same code, and what you want to do is to work on is basically the one loop operations, and then you want to do it is you will want that to run by multiple threads. So first you use OpenMP parallel, right? And then this is basic extra, or you want to know how many threads you want to use. And then it's basically the for loop here. You want to let the for loop to run in parallel. And then here you have where each will work on its own the partial area as the sum, and keep it private, right? At the end, you want to do the reduction is add all together. It's all this, make sure each thread add their own sum, and the sum is actually is only one sum. So you make it sure reduction, make it sure write it in the correct order. And then finally, where you get the mastered, and you get all the steps, you get the final results. So that's it. So this basically show you in this example is say we don't have much change to your sequential code, and the OpenMP, what you need to do, you add some OpenMP paths on top of your sequential code. And certainly for complicated questions or the data part, you need to think about more to work correctly. Okay. So now I want to talk about the components because OpenMP is a component directives. So to understand the basic of the components is important. So at SHARCNet, we have all kinds of components. The default one we use is entire component, and people still like to use the GNU component because well, it's more widely used and it's common all systems. And then there are other specific components called Pascal, or not, it's not a Pascal maybe, or it's change names. And then there's the PGI components. It's also a very famous one. Well, although all component companies agree with the OpenMP definition, and they do have different approaches. And then the commands used are slightly different as well. For internal component, when you compare your code, you need to add -OpenMP to enable the OpenMP part. Otherwise, the OpenMP part will deal as a command. So it will not. It will run if you don't add -OpenMP, and the code still run. It will run as a sequential code. And the GNU, when you use GNU compiler, you need to add -F OpenMP, and then PGI is simply the use -MP. So compare OpenMP code is as you compare your basic code when you use different compiler, use a different command. That's it. Okay. So when you run OpenMP code on SHARCNet systems, well, you need to have a basic knowledge of what type of cluster it is, and to make sure you run it right, because OpenMP code always supposed to run on one load. So it's how many threads can you use? It depends on how many cores the loader has. If a loader doesn't have that many cores for you, and your code is not going to run good. So SHARCNet has many clusters. So here I listed a few. For example, Orca is a cluster, and then load has different structures. Most of them they have 24, and some new loads they only have 16. So when you use the threads, the maximum you can use is 24. It will send you a job to 24 CPU nodes, and or you can specify less than 24 and less than 16. It could run on any load. And the SOA is a cluster. It all comes with the same type of load. The load has 8 CPUs, so you can only specify no more than 8 threads to run your code. Some others maybe have 24, like Redfin is a good cluster as well, and the Brown, most of the load is only have 8. So this is the thing. So when you ask 24 threads to work, submit a job to SOA, your code will never run because there's no such node on SOA. So your job will stay there forever. Okay. And then the components at SHARCNet, because the default component is Intel, and if you use a default component, well, we'll always encourage you to use a default component. But Intel is a good component, and you need to add -OpenMP to your code. Okay. If you use a Fortran component, where it's i4, it's the same thing. And for the GNU, if you use it, you need to add -F OpenMP. And at SHARCNet default compiler command, we use this. And if we use that, and basically we use Intel. So this is the command for you to compare simple code. Once you compare the code, and your code, and there's no any problem for you, and then you will submit a job to the threaded queue. And we have this threaded queue specifically for OpenMP OP thread code. So, and we limit the queue is basically all the processors, doesn't matter how many you ask, will be on one node, limited on one node, to make sure it's shared memory. So that's what we talk about. You need to to understand how many nodes that how many CPUs that load has, and then you use the right numbers. Okay. So what I talked today basically is a simple introduction and basically give you an idea. Well, OpenMP is the easy way to transfer or to convert your sequential code to run in parallel, to be parallel code. How is a partial parallelization solutions, and it doesn't run that big, depends on the hardware structure. It really works good for your application or not, and that's a lot of matter. And OpenMP doesn't just do loop parallelization. Also, loop parallelization is always a big task. In those days, they keep moving forward. Right now, the new definition is called OpenMP 4.0. It actually introduced some more interesting directives, and it will allow you to work on task parallelization, and it also works on deal with the data racing issues, and introduced many new features. And so if you now want to start from now on, you will need to take a look of the new specifications. Under the compiler, we have the newer compiler versions now pretty much support the new notifications. And also, if you go to this website, you can find lots of tutorials, and some of them are delivered by the developer and the group members. So they can do a lot of things. And also on the application side, we know there are several big application packages. They actually use OpenMP, and they run quite good. And the one used in chemistry, the name is called Gaussian, is a pure OpenMP solution, and it runs good at SHARCNet and used by many users in physics and chemistry. Okay, so I think that's basically all for today. And if you want to learn more, you can go to this is a reference for the OpenMP specifications, and this is very good documentations by one of the group members. And there are some books as well. And actually, we talk about OpenMP in SHARCNet summer school. And if you go to SHARCNet website, you can find some more details and more examples for OpenMP on SHARCNet web page. And if you have any questions, and or if you're working towards it, have any questions, you can approach us, and we can work together, and we can hopefully we can lend a hand, and hopefully you can do some parallel programming if you are new to parallel programming. Okay, that's it. Thank you, everyone.